Today, we will explore the fascinating world of attention mechanisms in neural system, focusing on the comparison between biological and artificial processes. We will see how adaptive control plays a crucial role in processing various stimuli. In biological systems, attention enhances the brain's response to specific characteristics like color, shape, and orientation. This involves both top-down attention, which is cognitive-driven, and bottom-up attention, which is sensory-driven. Key brain areas involved are the prefrontal cortex and the superior colliculus. Next, artificial neural networks mimics this biological mechanism through techniques like squeeze and excitation networks, which enhance specific features, and conditional batch normalization, which adapts network parameters dynamically. These methods significantly boost performance in visual tasks. Cross-modal attention integrates information from different sensory modalities such as visual, tactiles, and auditory cues. This integration highlights the flexibility and comprehensiveness of sensory processing in both biological and artificial systems. Understanding and bridging the gap between biological and artificial attention mechanisms has profound implications. It advances AI and machine learning, leading to the creation of more adaptable and robust systems. In conclusion, exploring these mechanisms provide valuable insights into the similarities and differences between natural and artificial attention. By applying biological principles, we can enhance AI innovation and adaptability.
Now I will explain about the journal review. The first journal is the role of selective attention on academic foundation and cognitive neuroscience perspective. This article is a Courtney Stephen and Devlin Balvillier article in Development Cognitive Neuroscience that explore the role of selective attention in academic performance. They propose that selective attention influences academic domains by modulating early neural processing. They suggest that temporal selective attention helps pass speech stream visual selective attention is crucial for reading, and selective attention support working memory during word problem solving. Adult studies suggest that attention training can enhance children's academic performance. The article is related to machine learning in the sense that it provides foundation for understanding the neural and cognitive machinery of attention, which could inform the development of more effective machine learning algorithm for attention training and personalized educations. Second journal is Cognitive Capacity in Self-Directing Learning, Evidence of Middle School Student Executive Attention to Resist Distraction. To put in simple, this is a study published in Acta Psychologica that explored the role of cognitive capacity in self-directed learning and its impact on learning gains. The study revealed that executive attention is crucial for middle school students to resist distraction during learning. It's a high-order cognitive process that allows students to focus on relevant information and ignore distraction. This is especially important for self-directed learning tasks that require searching, processing, and memorizing information simultaneously. Students with higher working memory capacity are better at resisting distraction and maintaining executive attention, leading to more efficient learning concept formation. Conversely, students with lower WMC struggle more with distraction, potentially using repetitive to manage cognitive load. Executive attention is closely related to working memory capacity, and cognitive load significantly influence learning outcome in self-directed learning scenarios.
Next, we will go through into the complex world of focused attention as it's related to both technological and natural system. This topic is critical for understanding how synthetic neural system and human mental processes work. Our visitor approach will draw from neuroscience, behavioral science, and automated learning. First, let's talk about attention. In both psychology and neuroscience, attention is central to understanding behavior. It's the variable regulation of limited computing powers in our brains, involving numerous and intricate areas. Basically, attention is based on our general state of consciousness and arousal controlled by the brain cerebral stem. Several neuromodulatory mechanisms play a significant role in attention. For example, dopamine is important for executive control and reward-based learning. Acetylcholine enhances sensory concentration and understanding, while norepinephrine is vital for awareness and attention to details. The thalamus and prefrontal cortex are the key players in attention. The thalamus interprets sensory data and transfers it to the cortex for the further processing. The prefrontal cortex especially is involved in top-down attention management, helping prioritize certain sensations based on the task at hand. There are various types of attention. The first one is arousal or consciousness, affected by neuromodular system and sleep-wake processes. Second is sensory attention, which filter different sensory signals, particularly visual. Third is visual spatial attention, focusing on specific spot in space, often demonstrated by eye movements. And lastly is feature-based attention, which focus on specific characteristics of stimuli like color or position. Neuroscientific research has identified specific brain processes underlying this type of attention. For example, visual spatial attention is linked to higher firing rates and fewer response variation, improving the signal-to-noise ratio. Improved gamma band coherence indicate better neuronal transmission, important for attention. In artificial system, particularly machine learning, attention mechanism has been inspired by biological processes. Artificial neural networks, or ANNs, incorporates attention layers to enhance efficiency by dynamically rearranging network representation and structure to focus on the relevant data. A notable example is the transformer model by Vaswani in 2017, which used self-attention to manage long-term relationships in text, leading to the advances in language modeling and automated translation. Understanding attention has practical implications in education. Insight into how attention works can help develop strategies for retention and acquisition. In AI and machine learning, attention mechanisms are applied in areas like autonomous driving and image recognition. Moreover, in reinforcement learning, this mechanism enhance cognitive and behavioral efficiency, mirroring how humans distribute attention to the optimal rewards.
Today, I will briefly introduce two key psychological theories in learning, which is social learning theory and behaviorism theory, and their application in artificial intelligence. Firstly, social learning theory developed by Albert Bandura emphasizes learning through observation and imitation. The core processes include attention, retention, reproduction, and motivation. An iconic study demonstrating this is the Bobo-doll experiment, where children imitate aggressive behavior observed in adults. In education, teachers model strategy like reading and problem solving for students to follow. In therapy, role-playing helps a client learn social skill or manage stress. This theory also parallel artificial intelligence, where attention mechanism is natural language processing and recommendation system model human behavior. Next, behaviorism associated with John B. Watson and B. F. Skinner focus on observable behavior. It involves two types of conditioning. First, classical conditioning as shown in Pavlov's dog experiment, and the second is operant conditioning, demonstrated by Skinner work with rats. In practical terms, behaviorism is applied in education through positive reinforcement such as praise and reward. In parenting, similar reinforcement technique encourage good behavior. In artificial intelligence, reinforcement learning mimic this process, optimizing neural network performance based on reinforcement outcomes. Both theories significantly influence artificial intelligence. Social learning theory emphasis on cognitive processes, mirrors attention mechanism in artificial intelligence, while behaviorism reinforcement principles are applied in artificial intelligence reinforcement learning models, enhancing their efficiency and adaptability. Understanding this theory not only provide insight into human learning but also guide the development of intelligent system in artificial intelligence.
One of the suggestions of this topic is enhanced artificial system. This means that integrate biological attention mechanisms to improve system effectiveness and concentration, and use CAMPAT model to predict fixation points and prioritize attention areas. For instance, apply saliency maps from human data to guide deep neural networks, or could use a teacher's saliency map for better attention distribution in artificial systems. The next point is application in various domains. One of the examples is image identification, which means to focus on crucial items to improve learning and accuracy. Moreover, in the medical imaging, the AI would learn from radiologists' focus areas for better analysis. Next, in natural language processing, which could improve text comprehension and generation. Lastly, in robotics, which enhance interaction with the environment. The next point is adaptive and flexible system. This means that we should understand circumstances, environment, and requirement for effective attention implementation. Or it is important to optimize top-down attention for processing valuable stimuli, which use cost-benefit analysis for decision-making and energy-saving modes. So it can ensure continuous improvement and sustainability through adaptive technique environment. The next point is biological knowledge integration. This means that use neuroscience information like the role of dorsal anterior cingulate cortex, which the study attention coordination in social species for AI improvements. It will enhance multi-agents interaction and coordination, such as robotic swarms and autonomous vehicles.
As a conclusion, we will delve into their complexity in biological systems, advancements in artificial networks, and their broad implication. Our research highlights the intricate regulation and dynamic flexibility in biological attention mechanisms. These interactions, managed by brain regions like the prefrontal cortex, optimize focus while filtering distractions. We have witnessed significant progress in artificial neural networks, integrating biological-inspired techniques like squeeze and excitation networks. This advancement enhance AI performance by mimicking selective enhancement and adaptive attention. Our findings extend beyond AI, enriching sensory integration, theories, and cognitive learning. They promise practical application in AI development and education, fostering more intelligent and adaptable systems. Lastly, studying attention mechanisms eliminates natural and artificial processes, driving innovation in AI toward greater adaptability and robustness. Thank you.